Hello, we are the IC Robotics Lab Robogripper team. Our technical directors are Paolo Stigagno and Chenzi Yuan. Our team consists of Rory Franks and Kyle Woodward, both electrical engineers, and myself, James Nelson, a computer engineer. The Intelligent Control and Robotics Lab is located at the University of Rhode Island and is a world-class robotics research lab. They are currently focused on robotic swarms, soft robotics, human-robot interactions, aerial robotics, and multi-robot systems. They are dedicated to contributing to a better future through developing cutting-edge robotic technology. The motivation behind this project was to create a robotic hand capable of performing complex gripping functions. Many tasks in modern manufacturing are repetitive and precise. This has led to an increased prevalence of robotics in industry. Our gripper was designed to be low cost and to act as an economic replacement for similar expensive hardware. Our anticipated best outcome was to create a functional prototype that could connect to the Rethink Sawyer arm and have it be able to grab a tennis ball and a screwdriver. We are happy to announce that we were able to achieve our best outcome. The gripper is able to be controlled from the same base station computer as the Sawyer arm, and while running, the gripper is able to communicate live sense feedback to the computer. Here we have a small demonstration of our gripper in action. The gripper waits to feel pressure on the palm and then begins to slowly close each finger. Once one of the sensors on the fingers feel enough pressure, the gripper stops and holds the ball. With the actualization of the gripper, there will be an economic benefit for the IC Robotics Lab. Being created through 3D printed materials, the cost of the gripper has remained low. The modular design allows for individual components to be adapted for a variety of uses without affecting the whole design. This also allows it to be easily equipped to other robots. With easy access to robotic grippers, the Robotics Lab will be able to advance its study of robotic manipulation, which in turn will allow them to attract more funding from the scientific community. Here is a functional block diagram that separates out the three main components that came together to create our functioning gripper. The aspect that I worked most closely with was the software integration. The Robot Operating System, also known as ROS, is an open source software for creating complex and adaptable robot behavior. It allows for a base station computer to communicate with the Robogripper and the Sawyer arm through what are known as topics. These topics are streams of information that are available to any robot or computer running on the same ROS core. This allows for easy integration with other robots that are used by the IC Robotics Lab. Here is a simple explanation of how the robots interact with the ROS core. When the Sawyer arm is turned on, it creates many topics, simplified as Sawyer controls. Similarly, when the Robogripper is turned on, it also creates topics, only two however. One is for controlling the gripper, and the other is for receiving the data sent by the gripper. The base station computer will send specific string messages to the control topics that the gripper will then interpret to move the motors accordingly. This pressure sensor topic is updated multiple times every second by the Robogripper. This allows for software on the base station computer to react to the most recent pressure felt by the gripper. The ROS Serial software library allows us to communicate between the Arduino that powers the gripper and the ROS core. It also allows a ROS launch file to be used to start the Arduino from the base station. We have developed a resource-efficient data transfer method so as to reduce the bandwidth used by the Robogripper. This lowers the amount of lag the base station computer may experience from the pressure sensor topic. Multiple control methods have been made that allow for specific behaviors of the Robogripper to be utilized. This is the software breakdown of how the Arduino reacts when a string message is posted to the control topic. The Arduino will read the message. If it does not recognize a given command, it will add a specific error value to the sensor readout so that a user may know that their command was not recognized. If a parameter setting command was sent, the Arduino first figures out which parameter needs to be changed, then sets the parameter to the specified value. If a move or pose command is sent, the Arduino first figures out which motors it needs to move. Then, if a move command was sent, all of the specified motors will move that value. If a pose command is sent, it assigns each motor its own specified value. It then moves each of them by that value individually. After the command has completed its task, The software will not run again until another message is posted. To create specific behaviors of the Robogripper, simple scripted programs can be made. Currently, two exist. One to cause the gripper to close on an object when it registers that the palm has been touched, and one to reset the position of the gripper. These programs were both made through the Python language, but the Robogripper package allows for the utilization of C++ as well. Next, my partner Kyle Woodward will talk about the physical modeling and the design realization.
The modeling of this project began with the design of a basic finger in CAD software. It has two flexible joints and a hole running through it for a carbon fiber string. Next, I designed mounts, which held the base of the finger as well as a motor to control its movements. After this, I designed another mount, which attached to the first mount to act as a knuckle joint. This whole assembly was attached to a base. Various other aspects of the design, such as the spacing of components and proportions of the gripper, were refined over time to increase gripping capabilities. The design is fully completed and has been implemented through 3D printing. 3D printing is an additive manufacturing process which constructs a model from a design in a variety of materials. In this case, a lightweight plastic. The gripper was purposely designed to not require support materials in order to increase efficiency and ease of construction. Various adjustments had to be made to the 3D printer settings of a Lulzbot printer to optimally produce the completed design. The built-in finger joints require the fingers to be printed in a high-quality setting with a precision of 0.2 millimeters in order to allow the joints to flex. The completed design includes a base with a palm and 3 knuckle mounts, 3 finger mechanisms controlled with a stepper motor, which pulls the carbon fiber string, and a case which contains an Arduino Mega and all the necessary wires and motor boards. The whole assembly is able to be attached to the Sawyer arm with 4 screws. And next, to talk about the use of the microcontroller and the assembly of a functional prototype is Rory Franks.
The microcontroller that serves as the source of control for the gripper is an Arduino Mega, which has a much larger range of pins to make use of than the typically used Arduino Uno. This was necessary for a gripper to have all 6 motors and 7 pressure sensors functioning together. The motors are attached in their designated places on the gripper and then wired to a breadboard that is then hooked up to the voltage pins and the digital pins of the Arduino. The pressure sensors are also connected to the same breadboard for power and are connected to the analog pins of the Arduino. The Arduino code that runs on the Mega takes the pressure values from the sensors and uses them to tell the motors to begin closing the hand. The gripper is designed to be simple to assemble. The 3 fingers are glued into a finger mount component which has an axle on the right side of them to be attached to the motor, which is then screwed onto the base component. This motor serves as the main point of closing for the finger, which moves the finger and dock in an opening and closing motion when spun. On the finger mount, there is a second motor with a spool that has a carbon fiber string, which runs throughout the finger to allow the finger to close itself. All 3 fingers are attached like this to the base, which is screwed onto the arm attachment plate, and the case, which holds all the motor boards, breadboard, and the Arduino Mega. The arm plate is then screwed onto the Sawyer arm whenever the gripper is in use. The Arduino Mega allows us to meticulously measure the pressure values that are sent to it by the sensors at a very fast rate. It is able to update those values at hundreds of times per second. The Mega is also capable of simultaneously doing this while controlling the 6 stepper motors and 7 pressure sensors, and moving them depending on the value of pressure that is given to them by the sensors. The code that is controlling the Mega, as we've gone over, is through ROS, which is hooked up to the microcontroller via the same computer that controls the Sawyer arm, allowing them to be able to be used together. To summarize our project, we first designed the modular components that allow one to edit and adjust the design of the gripper as needed. These components are the actuating fingers, all motor doxes and axles that the motors connect to, the connection piece which allows the gripper to be mounted onto the Sawyer arm. We then mapped out the wiring and pin usage for the Arduino microcontroller and put the motors and pressure sensors onto their designated spots on the gripper. Next, the Arduino controlling the gripper's interface with ROS, which is how the gripper will be controlled like the Sawyer arm is. Finally, the last step to our functioning gripper is getting the live feedback of updating pressure values being sent to the computer running ROS, which allows for the gripper to run its program and adjust the base positioning based on the values that it's receiving through the pressure sensors, and allow the gripper to begin closing and holding objects that are being pushed onto the palm. Lastly, we would like to thank our technical director, Professor Stigano, and the ELECOMP Capstone director, Dr. Sunak. Professor Stigano for helping us get every component and piece we needed for this project, and for giving us assistance on coding and design aspects whenever we needed help from him. and we would like to thank Dr. Sunak for efficiently running the Capstone program and making it very easy for us to keep focused on our work and plan out our schedule for the whole process to create a successful project.